Welcome to another podcast. In this episode, we're going to be taking a look at how to analyze the motion of a particle. And generally speaking, at this point of the semester, we are looking at applications of the derivative. And one of the biggest applications of the derivative is to the analysis of the motion of an object. You can think of it as a particle in physics, or you could think of it as an animal, an insect, or something like that in biology applications. You could think of it as sort of the movement of some sort of chemical reaction and the movement of the molecules involved in chemistry. There's all sorts of applications for this particular concept. And essentially we want to look at what's called the holy trinity, essentially, of physics, and that is position, velocity, and acceleration. So suppose that I have a particle whose position is governed by the function 1/3 t cubed minus 4t squared plus 12t, and we'll say that the position is measured in meters, and we'll say that the time is measured in seconds. So this gives the position of the object or the particle at any given time in seconds, and you can clearly see here that the position is 0 when t is equal to 0. So starting out at a position of 0, and we think of s oftentimes as being the displacement function, so it measures the position relative to the starting point. And in order to find the velocity, we know that the velocity is the derivative of displacement, or the derivative of position. And so the velocity in this case is, just using power rule here, would be t squared minus 8t plus 12. And this is measured in meters per second. These are the units here. And then finally, the acceleration is the second derivative of position, or the first derivative of velocity. And so taking the derivative of the velocity function up above, we get 2t minus 8, and the units here are length per time squared, or in this case meters per second squared. Now, all of that should be somewhat familiar to you if you've gone through a physics course. Mathematically, we're going to analyze what it is that we get out of having all three of these functions together. So there's a couple of questions that I want to ask. And the first question that we'll start with here, so question number 1, is when is the particle at equilibrium? So you say that the particle's at equilibrium is the same thing as saying that it's at its resting place or it's at its starting place. So equilibrium here implies that we're talking about the values of t for which the position is 0. So in order to solve for that, we basically take the position function, which is 1/3 t cubed minus 4t squared plus 12t, and set that equal to 0 and solve. I'm going to simplify this a little bit by multiplying through by 3. And then it's up to our ability to basically be able to factor this. I'm going to factor out a t here, which leaves me with a t squared minus 12t plus 36. And so looking at this factor gives me t equal to 0, and then this has a factorization of t minus 6 squared, so the other point we get is at t equal to 6. So there are two different times when the particle is at equilibrium. Starting off, it starts at equilibrium, which is to be expected, and then 6 seconds later it returns to its starting position. All right? Question number 2. Question number 2 is, when is the particle at rest? Now, I don't want you to confuse being at rest with being at equilibrium. Equilibrium means it returns to where it started, or it's at its starting location. At rest means not moving. So we say the particle's at rest when it's not actually moving. So not moving, that's a property of the velocity. So at rest means that the velocity is 0. So we need to look for points where the velocity is 0, or where the velocity function, which is t squared minus 8t plus 12, where that function is equal to 0. And so hopefully we can factor this. It factors into t minus 6 and t minus 2. So there are 2 points, t equal to 6 and t equal to 2, where we do not have any motion in the object. All right. Question number 3. When is the particle moving forward or backward? So movement is defined by the velocity. A positive velocity is equated with movement forward, while a negative velocity is associated with movement backwards. So positive velocity means we're looking for the values of v of t where they're greater than 0, and we just factored v of t in the previous question, so this is like saying where is t minus 6, t minus 2, where is this greater than 0? Well, remember, if you have two numbers multiplied by each other like these factors show, then in order for that multiplication to be positive, either both factors need to be positive or both factors need to be negative. So both factors are positive when t is greater than 6. You can clearly see that if t is greater than 6, this is positive and this is positive. So it'll be moving forward if t is greater than 6. So after 6 seconds, the particle's moving forward. Both of these factors will be negative as long as t is in between 0 or 2, and I'm stopping it at 0 to 2 because we're not considering what happens before the starting time. So we're starting everything at t equal to 0. But you can see that if t is less than 2, this is negative and this is negative, but together, multiplied, they're positive, so the particle is moving forward between 0 and 2 seconds. When is the particle moving backward? Well, that's when the velocity is less than 0. And so the velocity is less than 0 when t minus 6, t minus 2 is less than 0. And applying the same sort of logic as we did before, you get a negative number when one of them is positive and the other one's negative. And the only way for us to do that is to have t between 2 and 6. If t is between 2 and 6, then this one is positive, but this one is negative. It's not possible to have this one be positive and this one be negative on this interval. So these are our intervals over which we're moving forward. So this is the forward times, and these are the times in which it's moving backward. All right. The next question is, can we draw a diagram of what's happening here? So I'll write that in right here. So question number 4 is, can we provide a diagram of the particle motion? So this is a very common application of this. These are called state diagrams usually. And so here's what I want to do. We'll let this be the time interval on the bottom. And so we start off at time equal to 0. And at time equal to 0, our position is 0. And then you can see here we're moving forward for 2 seconds. And so I'm going to draw in t equal to 2 on this timeline. And so over the first 2 seconds, we're moving forward, and we move forward how far after 2 seconds? Well, I need to know what my position is after 2 seconds. So that's s of 2, and so I'll just do that right here. S of 2 is 1/3 2 cubed minus 4 2 squared plus 12 times 2. And if you multiply that through, you'll get 32/3. So my position after 2 seconds is 32/3. I'm 32/3 meters away from my starting position. So the way that we draw that in is we have a little dot here, and we'll have another. Basically, we show that it's moving forward in time, and then it's going to start to slow down in reverse directions. So at t equal to 2, what we notice is it's actually not moving at t equal to 2. And so the velocity is 0 there. It's kind of at rest at this point, but it's moving in this direction. Now, what happens between 2 and 6 is that the object starts to move backwards. So we start to go in the reverse direction, and the question is, when do we turn back around? Well, you can see that after 6 seconds we turn back around, so I've got to figure out what is the position when t is equal to 6. So I'll do that right here. What is the position after 6 seconds? And so that's just 1/3 6 cubed minus 4 times 6 squared plus 12 times 6. And surprisingly enough, if you calculate that value, you'll get 0. If you go back over here and look, it returns to equilibrium after 6 seconds, so we know it's back to this point after t equal to 6. So it returns back to its equilibrium of s equal to 0 after 6 seconds. So I want you to think about this in terms of the motion of this object. It took 2 seconds to travel 32/3 in the forward direction, but yet it took 4 seconds to cover that same distance going back. So it's moving faster on this interval than it is on this one where it's moving slower. So keep in mind the relative speeds of the object, or the relative velocities of the object on both parts. Now, after t equal to 6 seconds, so 7, 8, 9, it starts to move forward, so it's going to reverse its direction again, and at no point after that does it come back to rest. T equal to 6 is the last resting second, and it's just going to continue on forward from then. So this is a diagram of the motion of that particle. Moves forward from t equals 0 to t equals 2, moves backward from 2 to 6, covering the exact same distance, and then from then on it's going to move forward in time. Okay, let's do one more thing here. And these are really the important questions. The ones I'm about to talk about now are some of the more important questions for this topic, so make sure that you kind of understand what I'm doing here. Suppose I wanted to know what is the total distance traveled in the first, let's say, first 10 seconds. Okay, you got to be careful here. And what I mean by being careful here is s at 10 is the position after 10 seconds. And so s at 10 is 163rd meters. So did we travel a total of 163rd meters? Well, not exactly. Because notice we're traveling forward and backwards and forwards, and our position may be 163rd meters from where we started, but we might have traveled more than that by the time we get there. In fact, we will have traveled more than that by the time we get there. So how do we calculate it? Well, this is where the diagram of the particle motion helps. I have to add up each of these legs separately. So the idea is I add up 0 to 2, and so my distance traveled from 0 to 2 is the absolute value of the difference between my position at 2 and my position at 0. This turns out to be 32 thirds. Then I have to look at my position on this stretch, which is between 2 and 6. And so my position after 6 seconds minus my position at 2 during this stretch, well, I had to travel the exact same distance. So I traveled 32 thirds once again. And then finally, going from S6 to S10, I traveled from S6 all the way out to, well, if my position is 163rd meters, I go from S equal to 0 at 6 up to this, so it's got to be 163rd total meters traveled. So each of these is the total distance traveled on each of those legs, and so as a whole, the total distance that the particle would have traveled over the first 10 seconds is the sum of each of these. And so if you add up all of those, you get 224 thirds meters, which is approximately 74.6 meters. So that's how far of a distance is traveled over the first 10 seconds. Finally, the last question here is, rather than asking about distance, I want to know what is the total displacement. And here's what a lot of students will get question 5 and question 6 confused. The difference is this. We're moving forward from 0 to 2. So we add in the positive movement forward, but then remember we're moving backward from 2 to 6, so we subtract that distance, which makes sense because displacement-wise, after these first 2 legs, we're back to where we started. We're back at a position of 0. And then for the third leg here, we add on another 160 thirds. And so the total there is 160 thirds meters, which corresponds precisely to S of 10. This is nothing more than S of 10. So the question is, how do we find displacement? Well, the total displacement after 10 seconds is nothing more than S of 10 minus S of 0. That's what this is. So if you're calculating distance, you have to consider each leg separately, whereas if you're counting displacement, all you need to do is consider the starting location and the ending location and the differences between those. All right, this is all the types of questions that we might consider when analyzing the motion of a particle. Another thing that we could bring to the party here is talking about the acceleration of the object, which we really didn't touch on much in this video, but the acceleration is another thing we could try to analyze. But typically speaking, at least in the Cal 1 course, we're going to spend most of our time discussing position and velocity and their implications for particle motion. So it's probably a really good idea that you watch this video maybe more than once. There's several examples in the text that go along with it to make sure that you kind of have this idea down, because you're going to see this again both on quizzes and on tests. Got to make sure that you can do this coming out of this course. All right, thank you for watching.